Welcome, everybody. This is Professor Dan at the University of Colorado Boulder, and we are going to continue our shear and moment diagrams. So if you watched our last video, we saw that there were some common things. So we took a point load, and we saw how a point load goes into a shear diagram, goes into a moment diagram. And then we took a distributed load, like a flat distributed load, and saw how that went into a shear diagram and a moment diagram. Then we took a triangular load and we said, how does that migrate? How does that loading translate into a shear diagram and then a moment diagram? So this video is going to combine our loading. So let's say we have not just a point load, but also a point load and a distributed load. So one of the things that we talked about in our last video was how a discontinuity, a point load is a discontinuity. And in our shear diagram, that discontinuity becomes constant terms. And those constant terms became, in our moment diagram, up and down lines, linears. And those linears became up and down square terms or quadratics. And those square terms became up and down cubics. And it's because our shear is the integral, our change in shear is the integral of our loading. And our change in moment is the integral of our shear. So let's see how to combine when we have more than one loading. Let's see how we can combine them with what we know about these relationships. All right, so when we do our shear and moment diagrams, the first thing that we need to always do is find our reaction forces. So we have a pin reaction, so we have AY and AX, and we have a roller reaction, so we just have BY. Some of the forces in the X is 0, so we know AX is 0. Some of the forces in the Y, we have, let's see, AY going up, BY going up, then 27 kilonewtons going down. And then where does this 27 kilonewtons come from? Well, we know that we have a distributed load. We have our resultant force of our distributed load. And it's 9 times 3. It's 9 meters times 3 kilonewton meters. It's 27 kilonewtons as well, acting at the midpoint because it's rectangular. So that's 4.5. So we have a total loading of 54 kilonewtons. We take our moments about our point A, and we can see that minus 54 times 4.5, and we know it's negative from the right-hand rule, plus BY times 9 equals 0. Therefore, BY is 27. And we know AY plus BY is 54, so AY is also 27. So how does our reaction force act? Well, our reaction force acts as a discontinuity. So at the start, we always start our shear diagram at 0, but also at 0, we go straight up to 27 kilonewtons. All right, so in between 27, or in between our first point where we start at 27 and the midpoint, we go down. How far do we go down? So one of the things that we said is we can take the area under our load curve. So halfway down is 4.5, and our load curve is 3 kilonewton meters times 3 kilonewton meters, or per meter. So 4.5 times 3 kilonewtons, 4.5 times 3 is 13.5, but we know that it's acting negative, so we go down 13.5 kilonewtons. So here we're at 13.5 kilonewtons. Okay, so what happens at the midpoint? Remember, our reaction force, this FR, is just for calculating our reaction forces. Our resultant force is calculated to give us our reaction forces. When we do shear and moment, we have to take into account that this is a distributed load. And so that's what we're doing. But now we have this point load at 27 kilonewtons. So that's acting downward. So we go straight downward and we're at 13.5. We go straight downward, so 13.5 minus 27 is minus 13.5. So then what happens after that applied load? Well, what happens after that applied load is that we go down in a distributed way. So we go down some more. And we go down, we said if we have a constant term, a constant 3, we go down linearly. Okay. And how far do we go down? Well, what is the area under that curve? Well, it's 3 times 4.5, so that's down another minus 13.5. So now we're at minus 27. And so then what happens at B? Well, we're at minus 27. Hopefully we go back to 0 and we see BY is 27, minus 27 plus 27. We go back up and we close the curve. So that is how this works. So how do we do this? How can we prove to ourselves with an equation? Well, if our loading is 3 and it is acting negative, that's minus 3. The change in shear is the integral of minus 3 dx equals minus 3x. And then you can add a constant to that to get shear. What is our value at 0? Our value at 0 is our AY. AY is 27. So our equation for shear is equal to minus 3x plus 27. Okay, great. Now we can apply that everywhere there's not a discontinuity. So we know we're going down with a slope of minus 3. We know we're starting at 27. But we know our slope is minus 3, and when we have a discontinuity, we apply that by going straight down or straight up if it's acting up. All right, so we have our shear, and we also know that our shear is acting in a way so that when it crosses 0, we're going to have our maximum moment. And when we have our maximum moment, the one thing that we have to be careful about is that our equations are a little different. Our equations are a little different for when we're before that discontinuity, that applied load, and after it. So we just got to be careful. But we can see that in this particular case, there's a great deal of symmetry. We have some positive area and we have some negative area. So we know, let's see, what do we know? Well, what is the total amount of positive area? Where it's a trapezoid, where it's 27 on one end and 13.5 on the other. And then we see that, yeah, there's some symmetry. Our other trapezoid is going to be those same terms, but negative. Okay, that's good. So what is our total area? So we said before that if we know our total area, we know this point at the top, and we know that it is a squared term because we're integrating a linear term. Okay, so what is our area? Well, it's 13.5 times 4.5 plus 13.5, or 27, minus 13.5, which is 13.5, times 4.5 divided by 2. It's the triangle plus the square. All right, so 13.5 times 4.5 plus 13.5 times 4.5 divided by 2. I'm getting 91.25. All right. So can we check it? Well, let's try it. So if we know V is minus 3x plus 27, M, or delta M, is the integral of V dx. Okay, so our change in M is the integral of V dx. So that's going to be minus 3/2 x squared plus 27x. So our M is going to be adding the constant term to it, but our moments, we start at 0 because there's no applied moment. So let's plug it in and see if it works. Let's see, minus 3 divided by 2 times 4.5 squared plus 27 times 4.5. And we get 91.125. I think I missed a little one there. And that's kilonewton meters. So we can see that this is a way to potentially solve these types of problems. If we know delta V is the integral of our loading, dx, and delta M is the integral of our shear, dx, we can solve these problems relatively quickly and easily, even if we have these applied discontinuities. And if we have more than one applied discontinuity, we just need to be very careful with our starting and ending points when we do that. So I hope this helps, and yeah, look forward to seeing you in another video. If you have questions, leave a comment.